now, as an example, we had this identification of the compressibility field, where this was the compressibility, this was the deterministic description of the compressibility, and now we scale it, and the scaling factor is representing our uncertainty about the compressibility field. This is in general, the deterministic problem that we have seen, that there is a deterministic solver solving the problem with a finite element method for the nodal displacement, the pressure terms, and I get as a solution the nodal displacements, and from the nodal displacements I can get a general approximation for the displacement field, whereas I have measurements of the displacements in the vertical direction, so a u of zi, and at certain points. So from the deterministic problem, I get a vector of y, where I have ny number of values for vertical displacement. And this is something that I can compute from the model, and this is something that I can actually observe. And now what we are doing is we are trying to somehow propagate these uncertainties of the scaling factor. How does it change the solution or the quantity of interest y? And then in the next part of the presentation, we will talk about it, how we invert the problem when we have the measurement of this observable. Then how can we use these measurements to shrink our uncertainties or reduce our uncertainties of the scaling factor? So this is our task now. And this slide I have already shown you, that I need some prior description about my uncertainties of the scaling factor. And the way I described it, it's with a log normal field. I choose a log normal field because I want a bounded distribution, because the scaling factor cannot take negative values. So it doesn't make sense if I have negative values of the compressibility field. And I also choose a log normal because it's a very convenient distribution. It has a very straightforward underlying Gaussian random variable. So a log normally distributed random field I can get if I have a normally distributed random field and I take an exponential of it, and then I get a log normal field. Now this mu and sigma value will influence the mean value and variance of the field. So my underlying Gaussian field is correlated. Of course, it's correlated because the values of the scaling value cannot take completely different values in neighboring points. So when you have bigger compressibility at some point, then a close point to that will not have a significantly different value. This is what actually I assume, but in some cases this is not the case. Okay, so I say that my Gaussian field is described by a covariance function, whereas I use the Maten covariance with a certain parameter, nu c, which equals 2, and some correlation length, which is a quite big correlation length. So these two parameters gives me a relatively smooth field. So whenever I have some realizations of a Gaussian field like that, they are relatively smooth. So this is what I will work with. And as you see, I have this underlying Gaussian random field. And this Gaussian random field has zero mean in our case, and some covariance, which is described by this covariance function. Now, what I would like to have is, because now this theta Gaussian field is a field. So it depends not only on the actual realization, so not only on the stochastic domain, but also on the spatial domain. Now, this is very difficult to treat. And what I'm going to do, I will use the Karhunen-Löwe expansion that Professor Mattis explained you last lecture, in the last day lecture, and today's lecture too. So I will represent this random field in a separated manner, meaning that I separate the dependence on the spatial dimensions and separate the dependence on the stochastic dimensions. And due to the Karhunen-Löwe expansion, I can easily do that, which will take this form. So this is here the mean field. So the mean of my underlying Gaussian field, which I just told you that it has zero mean, because I'm only adding the mean of the field by this exponential term. So when I do this map, it will have a certain value, a certain mean value that I use for my prior distribution. Okay, so this is the mean field, which in our case will be 0. And this is a linear combination of products of random variables and spatial fields. Okay, these random variables from the Karhunen-Löwe expansion, I know that they are independent Gaussian random variable, which makes it ideal for an uncertainty quantification business, because if I have an uncorrelated Gaussian a set of uncorrelated random variables, then I know that they're also independent from each other. They form an ideal basis for RUQ analysis. Now, the equality actually only holds if this goes to infinity, so there's a small error here. And I truncate this expansion, so I take only L number of random variables, and this is how many fields I will have, deterministic spatial functions, and some scaling factor that corresponds to that. So let's see how I can fit this into this framework. Now I have the deterministic solver here, which gives me the observable displacements. And as input, I give the scaling factor. But the scaling factor can be also computed from the underlying Gaussian field. And I will make a further map, which is an underlying set of Gaussian random variables that are independent from each other. So this makes it somehow treatable that the actual input of the deterministic solver will be a set of random variables, just the same way as I had for the spring example. I had the stiffness and I had a mass. Now I have a vector of random variables, and I do the same way the uncertainty quantification as I did it before. Just I need some transformation before sending the Q parameters to the solver. So I need to transform it to the scaling factor, and then I can compute the FEM model. Now I introduce another map to make the things a bit complicated. And this is just the identity map. So in this case, psi and Q are exactly the same thing. So they are the same set of Gaussian random variables. I only introduce this additional random variable and step because I will use this as a germ. So I will use this for my expansion of the observable. Okay, I will make a surrogate model replacing this computationally expensive deterministic solver, which takes the values of psi and gives me the values of the observable, replacing this computationally expensive solver to something which is computationally very cheap. Now I introduce this additional random variable because the description of this surrogate model that it's using the coordinate system of the surrogate model, I don't want to change that. So this is something that I completely fix. This is a fixed number of random variables. They are Gaussian, and all the distributions are standard normal distributions. Q is the same. It's also normally distributed with standard distributions, but I will actually change this later on. When I want to do the inverse thing, I somehow need to update my knowledge. And what I will do, I will not update directly this field because it's complicated to do so, but I rather update this set of Gaussian random variables. So I will change this Q. So I want to have a fixed coordinate system, and I will only change this map, which maps me from psi to Q. But I don't want to change psi itself. That's why I introduced it. So now in the further slides, I will show you the previous steps, how I can define these maps. And then whenever I have these maps, I can start and generate a surrogate model, giving me from this set of Gaussian random variables the observable displacements. Okay, so how I do that? This is the Karhunen-Löwe expansion that I showed you. And I said these are some scaling factors and these are some spatial functions that I call eigenfunctions, because these functions can be computed from an eigenvalue problem, which is described right here. So these Ri spatial functions are the eigenfunctions of the problem, and these are the eigenvalues of the problem. Now, this is in the infinite dimensional space, so it would be difficult to compute this expression, and because of that, I try to somehow numerically discretize the problem to be able to code it directly in MATLAB. So the first approximation that I will make, that instead of looking for the eigenfunctions in this infinite dimensional space, I reduce the space of a subspace of functions that can be described as linear combination of these psi functions. Now I choose the psi functions to be some easy basis functions, and imagine here something like the finite element basis functions. Specifically, I only require with the derivations that these psi basis functions are nodal basis functions, meaning that at a certain point of some discretized domain. So I make a mesh, and over the mesh nodes, I have either values 1 or value 0. So this makes it nice for the description of the KLE expansion. If I can write my eigenfunctions as linear combinations of these nodal bases times some coefficient, then I only need to find this coefficient. Now I can write the same thing in a matrix form, where I put these psi basis functions in a horizontal vector. And this is a matrix whose columns corresponds to the nodal values of the eigenfunction. And I have as many columns, as many eigenfunctions I want to involve in the problem. So I said there are infinitely many. So this is as many nodes I have, as many spatial nodes I decided to have. And in the horizontal, the number of the columns is in the untruncated KLE expansion is infinite. And in the truncated one, if I choose L eigenvalues and eigenfunctions, then I will have L number of columns. With such description of the eigenfunctions, my eigenvalue problem is modified to the generalized eigenvalue problem that looks like that. Now the only new expression here is the C matrix. No, sorry, C matrix is nothing new. It is the covariance matrix. So now I have to evaluate the covariance at the given mesh nodes, at mesh node pairs, and G will be the Gramian matrix or the mass matrix, which is the integrated product of the basis functions. So this is the same as the mass matrix or the Gramian matrix in finite element method, where you have a set of basis functions and you integrate it over the domain. And this is computable with any finite element softwares, or you can also compute it on your, or code it on your own in an easy manner. So this is the covariance matrix. These are the eigenvalue vectors, the columns of this matrix. These are the eigenvalues of the problem, which is the same as the squared scale factor, and that's all. So this generalized eigenvalue problem can be solved by any numerical softwares like MATLAB or Python or whatever you wish to use. Okay, so this was my Gaussian, underlying Gaussian random field, and this is the KLE expansion of it, which with these approximations modifies to the mean field, which in our case is 0, as I mentioned, and the horizontal vector containing our nodal basis, V matrix containing the columns of the eigenvectors, the S are the singular values, let's say, or the scaling factors collected in the diagonal of a squared matrix, and X are the independent Gaussian random variables in a vector collected. I show you this in the matrix form. So this is how the matrix or the different matrices look like. So now I have a random vector, and this random vector is mapped to a Gaussian field. And now I separated the representation of this theta field to spatial functions and stochastic functions. Okay, now how do I do this? And I show you with the help of the sglib library package. First of all, what I need to do, the first step is to get a mesh, because I said I'm using for the eigenfunctions some nodal basis, which is defined over this KLE mesh that I show you here. And we actually have two different meshes for the finite element model and for the KLE. And this is just because of computational convenience. So how I chose this is that the finite element model that we had, it was using these quadratic elements. And I will need to send in the finite element model for every element one value of compressibility. So that's why I decided to have a mesh node of the KLE at the center points of the FEM element. And I decided to have triangular elements because that was the one that I had the implementation for. So this was just of computational convenience. So now you see here the finite element mesh, this center part of it, where the displacements are really significant, and these blue dots are the assimilation points where I had available measurements for the nodal displacements. So this is my defined mesh, and this mesh already defines a nodal basis defined over this triangle element, whereas I have 192 mesh nodes, and this is how many basis functions I have. Now, I should also mention that I extended the boundary with another set of points, and this is intentional because the KLE expansion gives relatively poor results on the very boundary of the domain, and I didn't want to include the boundary values in the finite element computation. So I made the mesh nodes also in these nodes, and then I excluded the results for those when I called the deterministic solver. Okay, this is the way I do it in SGLib. It's really just making some mesh nodes in the X direction and in the Y direction and make a rectangular mesh from it with triangular elements. And I can directly compute the mesh matrix with this inbuilt function. These are all SGLib functions, but you can also use some finite element solver to make the mesh and to compute the mesh matrix. It really depends on you. Then I compute the covariance matrix, and now the covariance matrix, I have to evaluate it at the different mesh node pairs. So according to my covariance function, the covariance function is the Maten covariance, which depends only on the distance in between the points. So if I have 192 points, then my covariance matrix will be also 192 times 192, whereas I always add up the I point with the J point, I compute the distance in between them, and I always divide by the given correlation length and plug that into my Maten covariance function, and that gives me a value for this specific place of the covariance matrix. If I, this is the SGLib way, because you can have access to the Maten covariance function, because there's a function for that in SGLib, and then compute from that the covariance matrix. Now, solving the generalized eigenvalue problem, there is a function for that, but it's also using inbuilt MATLAB functions, but it gives you directly the V matrix and the scaling factors that you put in the S matrix later on. So when I get from the eigenvalue problem the nodal values of the eigenfunctions, so these are these R spatial functions, an approximation of them. The first 9 functions are presented here. They look like Fourier bases, or a bit like Fourier bases. As Professor Mattis explained, they have a connection. KLE has a connection with the Fourier expansion. So these are the bases that I will use for the description of the random field. Now, I computed as many eigenfunctions, as many spatial nodes I had, but I don't want to use 192 spatial basis functions, because that would mean that this would be the number of my, just a minute, let me show you this equation here. So as many basis functions I have, that many random variables I will have, okay? If I choose L number of eigenbases, I will have L number of random variables. Now, I don't want this to be really high, because as I explained you, the curse of dimensionality, we always have to think about if the dimension of the problem is really big, then we have problems with the computation. We try to escape with as small number of random variables as possible. Okay, so I solved the eigenvalue and saw the eigenbases, and now I truncate, and I can compute the captured variance of the random field. And this is computed by summing up the eigenvalues, which is computed right here, multiplied by 100. So this is in percentage, and you can see a plot of that in this figure showing how the represented variance with different numbers of eigenfunctions involved is increasing. Now, don't ask me why I chose that to be 93. I don't remember anymore. Probably we had a reason, but we decided to represent 93% of the variance of the field, and that required the involvement of 11 eigenfunctions and 11 random variables. So now my expansion, the truncated expansion for the underlying Gaussian field is the mean field, which is 0. My spatial nodal basis functions, which is 192 functions collected in a horizontal vector. The V matrix, which has 11 columns and 192 rows. S is an 11 by 11 matrix in the diagonal collecting all the scaling factors, and X is a vector of 11 Gaussian random variables. Now, to define this set of parameters, I use the symparam set object, and I can create with this function a symparam set object which has only independent Gaussian random variables with the given, and I'm not sure if this is the variance or the standard deviation, but you can find it in the help functions. So I put input 11 1 values, and this will be the standard deviation or the variance of the Q parameters, because all the elements of this Q vector are standard Gaussian random variables. And this is what I need for the computations, that when what you saw in this framework, I have to define all those maps that were in that framework. So a map which maps me from the Q to the theta field is simply with the KL expansion, leaving out the nodal basis vectors, because then this will give me the values of the theta only at the KLE mesh nodes. And I can also define the inverse. So when I want to go from theta to Q, I can also do that. Okay, now I'm also defining how to go from Q all the way until the scaling factor. And these are the functions that are defining those maps. So this was the mean and the variance of the log normal field that I chose to be, which defines the two parameters of the log normal field. And then I can use the exponential function to map the Q value to this scaling factor through the theta. Okay, and the other way around. So these are all these descriptions of the different maps, and sorry, I pushed the wrong button. Just a second. Yes, here. So now I made the KLE. I have everything that I needed. All the maps are defined. And now what I do the uncertainty quantification exactly the same way how I did it in last lecture. There I had 2 random variables. Now I have 11 random variables. So the first step is to define for the surrogate model a basis, a set of orthogonal polynomials. So maybe some of you who can switch on microphone can tell me, if I have a set of Gaussian random variables, what basis should I use? Yes, exactly. It's the Hermite polynomials, because the Hermite polynomials are orthogonal with respect to the weighting function, which is defined the probability density of the Gaussian. So I use the Gaussian random variables, and because I have L dimensions, so now I need to have a multivariate Gaussian, Hermite polynomials, And in order to do that, I define some multi-index set. And you can see that I only have a linear set of basis functions. And we chose to do that because we could only afford a very, very low number of deterministic, of calling the deterministic solver. So we kept everything very low, and because the problem was only highly nonlinear, this gave us quite good results, even though we had only 11 terms in the dimension and only L plus 1, so 12 basis functions. We could achieve quite good results in the identification later on. This is just the definition in SGLib, how I define a multi-index set and how I define the basis. So you see here my 12 basis functions that I use for the uncertainty quantification. And I will need also the squared norms, which can be easily called from the SGLib function. Now I have defined this PCE basis, and I can call then the GPC basis norm function to get the norms that I will need. So now I will do orthogonal projection. And in order to do the orthogonal projection, I will need an integration rule. I use the sparse grid. Is it worth to use the sparse grid? And my answer is of course. If I want to use only a 2-point integration rule, then I would have 2048 points, because here the computational cost of the deterministic solver was really high. We didn't want to run this many points. So even though the sparse integration rule is not stable, we thought that our functions are really smooth, so we have no problems applying the sparse grid, and we had only 12 grid points in this case that we needed to compute. Okay, and this is a plot now of the scaling field itself. And namely the scaling field at the integration point. So I need to run the deterministic solver at the defined psi integration point. But as you remember, psi needs to be mapped to Q, and then Q need to be mapped to the Gaussian field, which is this term here, and then mapped to the log normal field, which is this expression here. And using this map, where this V and S is from the KLE problem that we solved, when we use this, we get the evaluations of the scaling factors at the different integration points. So if I have 12 integration points, then I will get 12 different scaling fields. And these are the scaling fields. These are the 12 different scaling fields that I will have to plug into my finite element computation. For every KLE node, I have a value of the FCM, and this corresponds to midpoints of the finite element mesh, so I can directly give for those elements the corresponding values. So this is a play with that to get rid of those additional boundary points, and then call the solver the finite element solver with those values that corresponds to center points of the FEM elements. Now you see that this is the way I compute. Sorry, there was this strange noise. Can you still hear me? Okay, hopefully nothing happened. This is the way I compute from orthogonal projection the coefficients, which is evaluated by approximating the exact value with a numerical approximation, where these are my PC basis functions, the Hermite polynomials that I showed you. These are the nodal displacements computed at the specific integration points, and these are the integration weights which are given by the integration rule. So its computation goes really easily with one line, and then I get a PC approximation of the deterministic solver, taking those psi values, the so-called germs, and mapping it to the values of the y. And this is how we will continue to the next part of the presentation. And I changed the slides, just a minute. Okay, and in this part of the presentation, I will talk about the identification, so the inverse method. And just as the motivation, I have already showed you what we are trying to do. So we will generate for an educational purpose a synthetic true value of the scaling field, which you can see here. And we can see if I assume some constant value, constant mean value of this random field and this log normal distribution that I presented you before, whether using the measurements we can update this true field or this prior knowledge to something which is similar to the true field. Okay, so this is what we will do. And I will also sometimes refer to this spring example that we had in last lectures and show you through these examples or the different methods that you can work with. So I will show you the brute force Markov chain Monte Carlo method, which is a sampling-based method. And I will show you the Kalman filter and its different forms of computations by sampling or by using the PC approximation. And I will also show you some nonlinear filters, which I will summarize at the end. Okay, so again, this was the general framework, what we did. So far, what we did the forward problem. We had some uncertainties of the input parameters, and we saw how these uncertainties are propagating through the solution. We saw how to measure statistics on the solution, like mean value variance or quantize, with the help of some surrogate model. And now we will see how we can use all these doing the inverse thing. So now I take actual real measurements that I present with these things. I either measure the temperature or some distance or a pressure or whatever I can measure, whatever is my quantity of interest or observable is. And then I use this knowledge to update the uncertainties of my input and hopefully shrink these uncertainties. And this is what we will do now. Now we will do the Bayesian framework that Professor Mattis explained to you. And the Bayesian framework is using the Bayes theorem, which states that our probability distribution function that we need, and it's important that what we will get at the end is not one value of the parameters, but it will be a whole distribution reflecting our updated knowledge, learning the measurements. So this is the distribution that we wish to get. The probability distribution of the scaling factor given a certain observation. This is Zm, is a vector of the values of the nodal displacements that we have actually observed. So we would like to get this distribution function, and the way we can get it, we need the likelihood which is the probability of the observation given a specific value of the parameters. Okay, this is the so-called likelihood that I will explain you with some small figure later on. It means how likely is it to observe the ZM value given a certain value of the scaling factor. Pi f is the prior distribution of the scaling factor. So this is reflecting our prior knowledge, what we had before, without learning the measurement. Okay, this is coming from some engineering expertise, either, or it could come also from other measurements. It depends. And what you have below is just simply integrating this whole thing that's on the top, so that I can get something that integrates to one. Okay, if I divide by that, then I scale it such way that the given term will be really a distribution function. So when I integrate it over the domain of the stochastic dimensions, then I will get one. Now, what is the problem? The problem, this prior distribution I have, that's no problem. I even have usually an explicit description of it. But the likelihood is not something that I have an explicit description of it. So it's very difficult to write this in a closed form. For very specific problems, you could write this analytically, but it's for a general problem, it's extremely hard to get some closed form to that. So that's the problem. And the way to handle that, first of all, I will change a little bit the formulation. I said I wanted to update the scaling factor because this is what I'm interested in. But as a general framework, what I will actually update this set of random variables. So instead of working with the field, it's much easier to work with the random variable. I will get an updated distribution of Q, and then I can map it to the scaling factor, the scaling field, okay? It's not a problem, and it makes the computation easier. Still, okay, I still don't have a closed form for the likelihood, so it didn't help me in that. And now let's see how I can handle this problem. Just another notation. So why do I call it ZM? So let's suppose QM is the true value of the input parameters. Okay, I have some true value of that. And I can compute the solution from the finite element model. I can compute the true response if I would have the true value of the input parameter. If I have the true response, this is not directly my observation because I have two things. One, there may be an error in my finite element computation, okay? It's a reflection of, or some kind of approximation of reality with many simplifications. So because of the simplifications and the numerical approximations and all the computational errors that I do because of the floating point operations, I have some error of this term here, which leads me to not exactly getting the true value of the displacement. So there's a modeling error, and there's also a measurement noise. Okay, I use some measurement equipment, and the measurement equipment has a certain precision. So now I'm putting these two things together. I suppose that both of these errors are additive errors, and they look like random noise. Okay, so they are not correlated, but completely independent from each other. So this is what I assume in the later analysis. So I have an error which I cannot get rid of, and my actual measurement or observation will be a sum of the truth and this error term. I can write it that my observation model is looking like this. This is a random variable where y is a random variable because it depends on q, which depends on the actual realization. And I also have an error term, which depends on the actual measurement error and the actual modeling error. So this will be the small epsilon, a sample from this noise model, and this will be a sample of the Y response model. Okay, so what the likelihood is, and this is what I promised you, that I will show you a slide about that. And the likelihood, as I said, is how likely is it that I'm measuring a certain value or this ZM value given some specific value of the parameter. So now I go back to the spring example because it's somewhat easier to explain you on that. So this is the time domain, and this is the displacement of the mass with time. And now you see a region, a blue region, which is the 1 sigma region. So this reflects my uncertainty because I have some uncertainty of the stiffness and the mass. This is how this uncertainty is propagating through the displacement as I go with time. Now I have a red curve which corresponds to the true response, okay? The true displacement field with the true value of the stiffness and the mass. I also have here another curve which corresponds to one specific realization of the Q parameter. Now let's say my actual measurements are this yellow point, okay? Now if I would only have this point here as a measurement, this yellow point, then my likelihood will be a function of Q, as you can see. It will be a function of Q. And the way to give it is that you take the probability density function of the error term, okay? This is something that you usually don't really know, but you just assume something, supposing something, knowing what the measurements were done with, what equipment did they use, the equipment, usually for an equipment, usually they give some error bounds and so on, how accurate the measurement device is. Now about your modeling error, this is a really tricky field and I'm not going to include that, but you can also suppose or add some additional uncertainties because of that. So I assumed here a Gaussian distribution, and I suppose that at the different points, these distributions are independent from each other because the measurements were taken independently. And I assume that they are unbiased, meaning that the mean value of the error is 0. And I suppose some variance of the error. So you can see this Gaussian curve. This is reflecting my measurement noise, okay? So if this is the measurement noise that I suppose, the likelihood will be giving me how probable it is given a certain value of Q. Now let's suppose that this certain value of Q is the one that is computed, or this curve is computed with this specific Q value. And then I get this displacement right here. And I center my probability density function at this point. And I see if this would be really the truth, okay? If this would be the truth, then how likely is it that I observe this value right here? So the further away I am from this value, the less likely is it to measure this measurement. So if I suppose that this would be really the true value of the Q, then if I measured this, it means that I made quite a big measurement error. So it has not so high likelihood. If my measurement would be somewhere here, then the likelihood would be much higher, okay? So this is my likelihood if I have only one point. If I suppose that the probability distribution function is such that these Gaussians are independent from each other, you draw a Gaussian at every center point of the blue. So at this section, you also put here a Gaussian distribution, and then you check here what's the likelihood. And you also check it here, and you take the product of them, because if they are independent from each other, then the probability density is computed from the product of the densities. So I just multiply up these probability values. Okay, so this is the likelihood. And this is showing again this framework that I have, and how to get this. Sorry, just a second. To set up the UQ results of the identification. So now I go back to our original problem of updating the scaling factor, and these are the things that I will need before that will be needed for the update. So I will need these maps, okay, that are described here, this F map and this exponential map, to get from Q all the way until Y. And instead of doing this, I will change it to the surrogate model that I made in last example. And I have something that's taking me from Xi all the way to the observable, okay? And I will show you why am I doing that. But this is just to prepare all the different identification, no matter which one am I choosing. I will just need those computations that I, in the previous slide, that I did for uncertainty quantification that I present you before, which is a surrogate model that I have and all these different maps. And this is how I define my synthetic measurement, okay? Just that you see how it's done. So I chose to have a true value. I mapped it to the Xi value throughout these maps that I have available. And I also defined a measurement noise model, which is this EM, which is a set of independent random variables with a certain standard deviation. And then I made a synthetic measurement, so just artificially created a measurement vector, which is the computed true value of the response, which I computed here by calling the deterministic solver and the true value of the scaling factor. And I added one sample of the measurement model. So this is a set of random variables. I make one samples of that, and this will be my measurement, my synthetic measurement. And then everything is comparable. And here you see all the assimilation points. I have 60 of them, and you can see how the displacement field is changing with the blue line, with the true value of the scaling factor. And then the red points are my synthetic measurement points. So these are my observations. The red points, sometimes the error is bigger, sometimes the error is smaller. It's sampled, so it was created with a stochastic way. Okay, and I also make another, which could be actually the same, but usually I don't know the exact measurement model. So I make an error model, which I will use for the update. And this is also a vector of Gaussian random variables that are independent from each other. Okay, so now we start with the brute force approach, the Markov chain Monte Carlo method. And I will start by the Bayes theorem. I told you this is the posterior distribution that I would like to get. This is the likelihood, which I have a problem of expressing, the prior and the normalizing factor. So how I will do it, I will, instead of computing this expression, what I will do, I will generate samples from this distribution. And I will use, namely, the a special random walk for sampling from this posterior distribution. And how it's done, it's explained in these steps right here and shown with the sjlib library package. So I do a random walk, and I make this random walk in the parametric space. If I have the random field, then Q is a set of random vectors with 11 random variables. Then I make this random walk in the 11-dimensional parametric space. And I need to choose a starting point, which is often the mean value of the prior, but you can choose also a different starting point. So now I choose it to be the mean value. And now I will make a so-called random walk in this parametric space. And how I make my steps, it's influenced by the so-called proposal density. So I define this proposal density, the density from which I sample, and this sample will decide where I put my fit in the next step. Usually I chose this to be a Gaussian distribution, but there are many sophisticated ways to choose proposal density. The ideal proposal density would be the posterior distribution itself, but of course I don't have access to the posterior density. There are also adaptive methods that are sequentially changing the prior distribution. I'm not doing anything fancy now. I only choose this to be some Gaussian random variable with a given variance. So you see here that I have the parametric space defined by this Q random vector, and I can have a random, no, not a random, a vector of the variances of these random variables, and I divide that or multiply that with 0.15 to shrink the variance, and this will be the variance of my proposal density of the Gaussian. This is just a thumb rule that I use. I use this sometime in between 0.1 and 0.3, something like that, depends. You have to experiment with that, what proposal density you're using. But this will decide how big steps you're making. If you choose a Gaussian, then the variance of the Gaussian will decide how big your steps will be. If the Gaussian's variance is small, then you sample from this small varying Gaussian, then you make really tiny steps. And then it will take you forever to discover the whole parametric domain, which is not good. If your steps are too big, that can make it too rough, and then you don't find really the good regions where the density function is where the density function is actually really taking high values, so that can be also problematic. So this is something you have to experiment with. So I started at a specific point, and now I sample from this proposal density that I gave you, that I told you that now I will use some Gaussian distribution. And this distribution is defined like that. It's conditioned on the actual value where I'm standing at in the parametric space, because I choose a Gaussian to be always centered where I'm actually standing. Okay, this is why it's a conditioned probability density. So I take a sample, and this will decide where I make my step in the parametric space. And now I made this step, and what I want to see that this is the posterior density, which should be still divided with the normalization factor. But I check that in the new step, and I check that in the previous step, and the normalization factor will be the same, so I can get rid of the normalization factor, which is a big advantage. So I don't have to care about this term right here. I only need this term. So I sample from that, and if I can compute the likelihood and the prior at that sample where I was and where I made my step, then I can see whether the probability density, the posterior probability density has increased with this step, or it has, or it got smaller. So at the point where I'm standing, I'm computing the posterior probability, and then I make a step. I check what is the value of the posterior probability there, and it will depend on the ratio of these two whether I will make the step or not. If in the new step the posterior density will be higher, then I will definitely make the step, and then this new step where I'm standing, this will be another added sample point to the samples. If it's smaller, it depends on the ratio. How smaller is it? If it's a lot smaller, I will accept it with a small chance. If it's not so far away from the initial step, the posterior density, then I will accept it with a high chance. Okay, and because of that, I compute this acceptance ratio, which will be the ratio of the two posterior probabilities. And from this alpha, what I will do, I will just draw a sample from a uniform distribution from 0 to 1. And if it's smaller than alpha, I accept it. If it's bigger, I don't accept it. And this way, I assure that I accepted with alpha probability the step. So it's not good if I would only make steps in the higher probability to the regions where I have higher posterior probability, because I need to have samples everywhere, more samples where I have high probability, but I need some samples also where I have low probability. So this assures that I also have some few number of samples where I have low probability region. Okay, so a question, how do I evaluate this? Okay, this is the way I will do the random walk, but okay, how do I compute at a certain value of Q the likelihood and the prior density? So the prior density is really not a problem. This is a density function that I decided what it is. I defined its probability distribution function too, so I can evaluate it at any parameter values. Now the likelihood is the likelihood that I actually showed you. I need to use the probability density function of the error. Just a minute, I go back here. So I need the probability density function of the error, and I need the difference in between the response computed at the actual value of Q and how far is it away from my actual measurement. Okay, these are the things that I need to compute here. So the likelihood is the probability distribution function, which is a Gaussian. That's why I have here this exponential and this term here. What is here I have the covariance of the error matrix. It's a diagonal matrix in this case, because I said that all 60 measurement points are independent from each other. So I just have diagonal values because I have an uncorrelated set of random variables. And I need to evaluate this density function at this difference, okay? The response at my either the Q prime or the actual position Q. I need to compute the displacement knowing the scaling factor. And this is my actual measurement. I subtract one from the other, and I evaluate this density function. So this is what I need to do. So I always need to compute the response given this value of the parameter. So this means here I need to actually run the deterministic solver. Now, if I make this random walk, it will converge really slowly because it's a Monte Carlo method. So as I showed you for the basic Monte Carlo method, this is also going very slowly. And if it's going very slowly, then I will need lots of evaluation. And it often happens that I'm stuck at a certain point of the parametric space because I started at a parametric value that corresponds to a low posterior probability, meaning that that this value is not very probable given the actual measurement. So it's very far away from the true value probably. And if I'm standing at a point such as that, then I need to wait until my step is enough big and in the good direction to go to a higher probability region, and then my random walk starts to accelerate. So I can get stuck for a while, it can happen, and I need lots of evaluation. So if I would need to run a FEM solver, which is very expensive, a nonlinear model with millions of mesh nodes, this is something that we cannot afford. But if you succeeded to make a good proxy model, a good surrogate model that we did in the previous lectures, then we can use this proxy model, which is right here. So this is just the Xi, okay, my germ. So I had a PC expansion of the Y random variable that can compute my observable with the help of this surrogate model. And then it goes with just evaluation of polynomials, which goes extremely fast. So that can make a really fast random walk, okay? And this is just the SGLib code to define the likelihood function. And you see it's really easy. So I worked hard to get the GPC, or sorry, the PC coefficients of the displacements. This was my PC basis. And I create a function which takes just these Xi values and evaluate my Y. And then I define a likelihood function which takes the difference from my actual measurement to this from this Y. And now I want to use the Q random variable because I want to make the random walk in the Q space. I don't want to update the Xi, I want to update the Q. Okay, so that's why the likelihood function looks like that. And if I do this random walk, and now I show you the case of a scalar problem, so I only have one random variable because I suppose that I don't have a random field, but I just have a constant value of the scaling factor. And then this is how the random walk will look like. Now you have zoomed out, this first part is zoomed out here, and you see that I had a bad start of the random variable. But after a while, I made a big enough step, okay, to get started in the right direction. And then after a while, it looks like a white noise. And whenever it looks like a white noise, this is perfect. It means that it really converged to some kind of distribution, and it stops here oscillating around this value. Now this red value is the true value, and the blue is the different sample points with the random walk. Okay, so you jump around the one-dimensional parametric space. You start at the mean value 0, and then you try different steps from here, and then you find, okay, if I make a step big as that, it got better, so I made this step. And then here I made these smaller steps, and most of them got accepted. Maybe there were some bigger ones that didn't get accepted. Then the sample is repeated there. But from here on, you see it looks like a white noise, and often they look at the acceptance ratio. So in the region where you have something acceptance ratio, there's a rule of thumb that it should be around 0.3 or something like that. I don't remember the exact number. Monte Carlo guys know this by heart. I don't. But it's good to check how the acceptance ratio is changing, and when you see that it's around this value, it's good. Okay. So what I do at the end, if I can look at the random chain like that, I know that, okay, this part It's really just depending on that I started the work at the wrong point. So something from here on, it can be considered to be all samples from the posterior distribution. So I choose this line here at the third 100th step, and I cut everything out from the samples here, because this part is the so-called burn-in period. Now it's very difficult to know what's the burn-in period, how many samples you should throw away to get a good approximation or a good set of samples. But this is the way the Monte Carlo methods are. Okay. And then if I have samples of the Q, I can map it to the values of the scaling factor with the maps that I define. And you see really that with the plain vanilla Monte Carlo method, the code is short as that, so it's really done in an easy manner. Okay, so now this is the presentation of the distribution plotted from the kernel density estimate. So the kernel density estimate is an estimation of a probability density from sample point. And you see here that this was my prior distribution, which is really flat. So I was really uncertain about the scaling factor's value. And this is the samples distribution of the updated from the updated posterior distribution. And you see the true value here, and I zoomed out this part, and you see that this is the true value, and this, sorry, the black line is a true value, and the dotted line is the mean value of the posterior distribution that I get from the samples. So knowing that this big uncertainties I had, and I got pretty close to the true value, this was a quite good identification for the scalar case. Now, don't accept to get exactly to the true value. This is not something that you should require to have. Even if you have synthetic measurement, you shouldn't get exactly to the true value, because you have a measurement noise, okay? And the measurement noise is influencing what your updated thing will be. So it will learn from the measurement, and it will learn from the model, and then you put some confidence in your model through how certain you are in the input parameters. So we put here a quite big uncertainty, so not so big confidence in the model. And then I put also some confidence on the measurement through the measurement error. This is what describes how much I believe my measurement is the measurement error. How big is the variance of the measurement error? If I know that these are really, sorry for the word, but shitty measurements, then you choose big value for the variance of the noise, and then you cannot that much update your knowledge, because you learn something from the measurement, but you still trust more the model. And how the prior probability will change, it depends on how much you trust your measurement. If you really trust the measurement, and if it's telling you something completely different than your prior distribution, then it will really shift it, okay? So this is the way it works. And this, as Professor Matti said, there were some discussion whether you can use the Bayes theorem and I mean, for epistemic uncertainty, because it's really a subjective way of thinking. What you do there is you actually put your prior belief about the parameter and your prior belief about your measurement, how much you trust them, or what you know about them. But this should really reflect your knowledge. You actually put your subjective knowledge about the problem inside the computations. And if you're wrong, you will get wrong results, okay? There's no wonder. So this will be a reflection of what you think. And this is a good thing, because actually, if the more information you have, these informations you should all put inside the model, okay? There are always theories that you put there. You also know that you make some simplification. Then you can add some modeling error, because you know that you made some error in the modeling part. Or you can make measurements and use those measurements, but if you know that you don't trust that much those measurements, you should put this information inside that. And this is how the updated solution will be reflected, or your belief will be reflected in the updated distribution. So this is an example for the random field when I had these 11 random variables, and here I only plot the random walk of 4 of them. And you can see that here it's quite difficult to say when it actually starts to converge to a specific distribution, because it's a high dimensional problem, and with this 1D plot you cannot really see what's going on. Maybe these blue curves, they tend to go and oscillate around those true values of the parameters, the blue lines, but also the orange. But for example, this brownish color, it's really oscillating here and there. So it's difficult to know which part is the burn-in part and how long you should go with the walk. Now, when you actually plot it in all the different dimensions to see a little bit more from this high dimensional space, and it's really nice. Unfortunately, I don't have this video of how the random walk can look like. So what I like to do is not to make one chain. So it's not like I start at a certain point and make those steps, either accept or not, but I send out a whole army to the parametric space, like, I don't know, 1,000 people, start at the mean value of the Q parameter, and they all start their random walk. And then when you have a plot, for example, paired up with different values, then you can really see when it starts to converge to a specific distribution. But of course, it's high dimensional, so it's two-dimensional plot doesn't give you all the information, but it gives you a lot of information often. So you can see that actually they are all tended towards a certain region, all the points, and you can see how the probability densities of Q were updated from the dark blue to the light blue line, and how far away they were from the red point, the true value of the parameter. And now if I have the updated version of Q, I can compute the mean value of the field, for example. So this was the true random field, the scaling factor field. And this is the mean computed from, I have samples, I only have samples. So I will map all the samples to FCM. Then I will have that many field realizations. And then I take its mean values, and then I can plot this mean field of the scaling factor. And you can see they look quite alike, okay? You also see a 3D plot. They are not exactly the same, okay? And the reason is somehow presented here. So this is the standard deviation of the updated samples, and this is the error that I'm doing with the mean. Okay, the mean is not always a good thing to have, okay, because it depends on the distribution. Okay, but in this case it was not bad to have the mean value. And what you see here, that the errors are bigger in these lighter regions, what you make with the mean approximation. And you see here a plot of the assimilation points as well. So those were the 60 points that were assimilated, and their colors represent how high the displacements were at those points. So because there were no displacements here, of course, you cannot learn anything about the compressibility field in those regions where it doesn't displace, right? If you have no deformations, then you cannot learn about the compressibility. So this makes sense. So from these measurements, what I could learn is rather about this region where the error is really low, so I can get a very good estimate of the compressibility field. So here you see the prior, okay? The prior was a uniform, was just the mean of the prior was a constant value. And this was the 1 sigma region. So I was like it's somewhere around 5.5 plus minus this value. This was my prior belief, and this is my posterior belief, the mean and the 1 sigma region. So I know how certain I am about this mean value, and it seems it's quite close to the actual true value. Okay, and this is another example for the spring, and you can see that this was the response surface. So as I explained you, if I have one measurement of the displacement, so here this is the stiffness, this is the mass, and this is how the displacement of the mass depends at a certain time on the values of K and M. And if I measure a certain value of measurement, then you see this is this plane, and you can see that there are several values of K and M that can result in the same displacement. And this is what I get from the sample. So it really discovers all these good points of good combinations of K and M, which lie along a line, of course, because they depend on the ratio of K and M. But you see that from the Markov chain, the random, when I plot the chains, it's difficult to see where to stop the burning period and when you can actually stop the simulation. Okay, and now I'm switching to Kalman filter methods, and I think I'm quite late. Okay, I have 8 minutes, so I try to rush up. Okay, so I have here the same thing that I had before, where this is my likelihood and this is my prior distribution. And now what I suppose is the following, that my observable Y can be written with a linear map. So this is a matrix H, which is the observation matrix. And it says that I can reflect my observable as a linear map from Q to Y. This is really something that's not true for any of these problems that I showed you, but let's suppose that it can be linearly represented. Then here I have my likelihood. Sorry, this is the posterior. So probably in the next slide I will have, no, here, sorry, here I have the likelihood. And in the likelihood, I have the deviation of the measurement from the actual response. And now this actual response can be written as H times Q. Okay, that's the only change in the whole setup. And Kalman filter says, the Kalman theory, that the posterior distribution looks like that, which is because this, if I have an underlying Gauss measure, so Q is a vector of Gaussian random variables, then because this is a linear map, then Y will be also Gaussian. So then the update will be also Gaussian. So the theorem says that my updated distribution will be a Gaussian distribution with mean value mu q prime and with variance CQ prime. Now the CQ prime can be written as the covariance of Q prime Q prime, which equals to this expression here. And the mean value can be written also as an expression depending on this K, which is a matrix, which is called the Kalman gain. Okay. The posterior random variable is just then can be written as Q prime, which equals to Q plus the Kalman filter. And here I have the deviation from the measurement model to the actual measurement. Okay, so this you can actually prove if you have a linear map to the posterior from the measurement model Z, because this is just multiplied with the matrix. If you have such expression, you can show that the mean value of this here will be really this expression here, and the covariance will be this expression here. So this is the Kalman filtering, where you get a posterior random variable with a linear map like that. And the Kalman gain is expressed from the covariance matrices from this term right here. So from this posterior, you can derive the covariance and you can derive the mean value, and you can prove that this random variable has mean value like this and covariance like that. And because it's a Gaussian random variable, because the underlying measure was Gaussian and because everything is linear, then a Gaussian is described totally by its first two moments, so the mean and the covariance. So then I have an updated random variable. Okay. Now if I don't have a linear map, but in my case, I have an abstract formulation, right? This G is really not something, it's just, I called it G, but I don't have this as an explicit operator. I don't have a closed form how the Y is depending on Q, okay? So it's some observation operator H. Then what I can do is that this is not true anymore, but what I can say is that I can sample from these random variables, okay? I make lots of samples of Z, and I make lots of samples of Q, and then I can compute these updated things, and the K, the Kalman filter, which depends on these covariances. So the covariances I also compute from samples. So if I have the germ psi, then I can have samples of Y, okay, which is the evaluation at this germ of the observable. Please notice that this is something that we have from the surrogate model directly. And this is its mean value. And this is the covariance matrix that I get from the samples. And like that, I can also get an estimate of the updated random variables. Okay. But it's a Monte Carlo way of do that, and you need lots of samples, and it's still computing it from this term, which really assumes this linear dependency, which we don't really have. Okay, but we can actually do this with the help of the PC that I already told you, okay? Because the Y of psi j is just simply the surrogate model. Q of psi j in the beginning is just the identity map. And this is the error term. I didn't mention that the error, I can also assign some germs to that. So I can make an PC expansion of the error term as well, though they are Gaussian already. I can write it with the help of a PC term. And then I get some estimation of the covariance matrices, and I can directly do it with the help of the PC framework. But what's more interesting, and I'm going to skip this now, how I do this with the samples, is the PC-based Kalman filter. So what I can do here, and I check the time, and probably I have 1 minute, so if it's okay with you, I will go for another 5 or 10 minutes. I try to really finish fast. The PC-based Kalman filter starts from the same equation here, okay? And what I do is that I don't do any samples and I don't evaluate the covariance, or I will evaluate the covariance, but I do everything without any samples. And the way to do that is that I already have a PC expansion of Q. I didn't have one of Q. I had only one of Y, but I can write one of Q and I can write one of epsilon, okay? Now, the one of Q will be just simply something simple as that. If psi is, it's the identity map. So I have to put the PC expansion of the identity map, which is really something simple. And here I choose a set of basis functions for the error term too, only linear ones because I don't need others, because epsilon is only a set of random Gaussian random variables. So then I have the PC coefficients here. I have 0 mean of epsilon. So here I have zeros. And here I have just simply the standard deviations of the error term. And this is how my basis functions will look like. The y, I did it already. Okay, let's see that I have the 1D case. So I have only one random variable. So one xi. And then this is the PC basis that I used for the approximation of the solution. Okay. Now I have to somehow be able to compute these terms. So I have to add these variables together and so on, but they don't have the same basis yet. Okay, this one and xi is the same xi as I have here. So this is the same xi as here because the y depends on those xi variables that the q depends on. So this is the same basis, but I only need here the linear term and the constant term. And here I also need these higher degree terms. So somehow I need to put those together, and I also need to put it together with this basis. So I extend my basis so I can write a common PC basis for all these three random vectors. And this is the way to do it. So it's really easy. I just collect all the xi's, all the basis functions that I had for q and that I had for y, which are all these xi terms until here. And I also had a PC expansion of the error that depended on another set of Gaussian germs. And I write them here. I have 60 of them because I have 60 assimilation points. And now I can update these or rewrite these coefficients such way that I extended the basis. So of course the expansion of the q will be just a 0 and 1 corresponding to this 1 and xi, and these are all cancelled out. I don't need that for the description of q. And then for my PC expansion of the solution, this was my original basis until here. So if I don't know, I have maybe 6 bases here, I'm not sure, or 6 bases here. So I will have 6 columns here that are non-zero, and the original PC coefficients are here. And here I just have some additional zeros. And I can as well write the measurement itself with the PC form. The measurement itself, so the actual value that I'm measuring, it's a deterministic value. It's not stochastic. But I could write it with this basis. All of them are 0, the coefficients corresponding to everything except the accepted value, because it's a deterministic thing. So I just put the ZM vector in this first column, and the rest of them I just cancel out. So this is the common PC basis. And then I can write what this expression is actually. And this you can see here. And it's just a simple PC algebra to put them all together. And then at the end, what you get when you add them up, is the PC coefficients of the updated random variables. So you define an extended basis. Now, please note that the basis will grow as the number of measurements grow, okay? So my description of the posterior will be in this extended basis. That dimension is the number of the independent random variable that describe the forward problem, plus the number of the random variables that describe the error term. And these dimensions will add up, and this added dimension, I can make a PC approximation of the updated random variable, and I will get directly from this equation here the PC coefficients of the updated random variable. And I skip the computation here. And I just tell you a few, so you can also see the solutions here with the Kalman filter. Now the posterior distribution is somehow off from the true value, but I got still a good update from the prior distribution. And the reason is because I used Kalman filter, which assumes this linearity, which is not true in our case. So to make it somehow better, to improve it, I can have a nonlinear map from the measurement to the updated random variable. And I do this, as Professor Mattis explained, from minimizing in a mean squared error this difference. And I do that by an estimator, okay, which is estimating my updated random variable. How I get from the measurement itself, the measurement model itself, to the Q value. So somehow I'm reflecting this inverse problem with this phi estimator. There I approximate the phi estimator instead of some infinite dimensional functional description. I try to find a solution in a subspace spanned by some linear combination of basis functions. And here I use also polynomials for the descriptions in this example. But you can use, as Professor Mattis said, any other functions. And now I need for the estimator these coefficients. And from the minimalization problem, it turns out that these coefficients can be computed from a linear system of equations where the A and B term are described here. These are integral terms over the stochastic domain, but please notice that the stochastic domain is the coupled domain of the input random variables and the noise. So the same way how in the Kalman filter we had. Now the stochastic dimension is increased. As many measurements I have, as many independent measurements I have, this is how many dimensions I have to add to the whole problem. And I can approximate this integral with some numerical integration, but this can grow really high, this dimension. As I said it, to compute a numerical approximation of an integral, when the dimension is really high, it's cursed by the curse of dimensionality. So it's tricky how to do that. But there is some way to use low rank approximation, what Professor Mattis explained you, also for the output. So for the response itself, and then you can reduce this dimension, and such nonlinear filter can be computed in an efficient way like that. And you can see how when I choose the estimator to be higher degree. So when I use a linear term, I get exactly the same thing what I had for Kalman filter, because this is the linear estimator, the Kalman filter. This minimum mean square estimator's linear version is the Kalman filter. And then as I increased the degree of the polynomials, I could get a more accurate result. And this was it. This is the results for the field. You can check all these examples on this website that I gave you. And I'm not going to explain you this example. Maybe just a fast way. If you have some posterior distribution that should look like that, like this, because this is some measurement, and this is the response surface, and this is the underlying prior. You can also get a quite good result, not so good result with the linear filter, but there can be such measurement when I choose the prior distribution to more center around this cylindric surface, then my true base distribution should be some probability distribution all around this ring. And this is when the minimum mean square estimator has a real problem getting a good estimate of the posterior distribution. So you see the samples are everywhere. So to sum up, MCMC has the disadvantage that it's a Monte Carlo method. It has its low convergence rate. It's sometimes difficult to recover multimodal distributions. So multimodal distributions are distributions with not only one peak, but several peaks. So something something like this. For example, this is a multimodal distribution, because you have to jump over this and that point. But you saw in the spring example, if you choose the proposal density right, you can get those set of points quite well. But it depends on the proposal density. That's also difficult, how to choose the proposal density, and there's many playing around and trial and error things. How to choose the burn-in period and when to stop the iteration. So these are some difficulties with the Monte Carlo method. And the nice thing about the PC-based Kalman filter and the higher degree estimators, that they are given in a functional form. So you have a functional expression of the posterior distribution. When you want to repeat the update because you have some new measurements, it's really done easily, because when you have only samples, then it's tricky how to get from the samples to a new update procedure. But when you have a functional representation, then you can compute anything from it. So that's a really nice thing about these filters. But the Kalman filter has the disadvantage that it has this linear restriction, which limits the solution. You can do it in a sequential way that is shown by Dr. Bojana Rosic. You can check her papers, or you can go to higher degree estimators, which will also only ensure, as Professor Mattis explained, to recover the conditioned mean and not the whole distribution. And in a case, if you have this B-model distribution, of the posterior, so something like like that, then actually the mean value of the posterior will be really a bad value for a 1-point estimate. So you really have to watch out for it. And ideally, what we would like to have is recover the whole distribution. And to recover the whole distributions, in the Outlook you can see, you can try different methods, like trying to recover higher moments, as Professor Mattis explained, not only the condition mean, but also the condition covariance and higher moments, but then blows up the computation. So it's a quite challenging problem. Or you can also run into the problem that polynomials are not ideal for the inverse map. If the forward problem is a polynomial, then the inverse should be more like rational functions, or you can also use neural networks and so on. So you can change the basis for this. And the other thing is was also mentioned by Professor Mattis. It's also a question how to deal with aleatory uncertainty. So there are many problems when you have the stochastic nature of the problem, when it's really a stochastic thing, like I don't know how the waves are forming and loading a structure in the sea and such things. And or when you have several similar structures, for example, and this is how you try to update and get a posterior distribution. And then your truth will be a random variable, and then you will try to treat the parameters of those random variables as random variables and update those random variables. So for example, if you have some wind load that has a distribution, something like that, then you take the mean value and you take the variance which describes that, and you take the mean and the variance as two random variables, and then you're identifying that. And this is something that we have done for the snow load problem and so on. So look into the literature if you would like to know more about that. This is where I close, and I'm sorry I went way longer, 15 minutes. Sorry and excuse me for that. But I hope you learned from it and you had a good cover for all the theories that Professor Mattis gave you. I think you're really lucky to listen to that, and I hope I could cover a little bit the engineering part, how it's actually done, and if you're interested, then you have something to follow and to learn from. And thank you for the attention, and if you have any questions, please, this is the time to pose it. Could we use optimization algorithm instead of a random walk? I told you can always do optimization. So what you do when you do optimization is that you get one deterministic value. So the whole purpose of this lectures were to do it in a probabilistic way, not to get one random variable, but to not to get one random variable, but to get a whole distribution that reflects your updated knowledge, learning about the model, building inside your prior probability, and this can lead actually to very similar one-point estimates if you do an optimization problem and if you do the Bayesian way. Depending on what you use for regularization term when you do optimization. So when you do it in a probabilistic way, it's somehow like some way regularizing the problem, which is in nature ill-posed, because you can have several values that corresponds to the same output. Did you get an answer for your question? Okay, good. So the classical way is to do optimization, and the more advanced way, I would say, is to do it the probabilistic way, which gives you more information, and then you can still choose a one-point estimate, which you think is a good point, a good one-point estimate.